Hello, fellow Chem 332 students. My name is Ben, and I'm going to be doing a P3 replay of P3 number 15. So let's go into the archive and go down. I'm going to do number 2 because that was the one that I did in my discussion. And I'll tell you guys right now that I did not get this right the first time through, but I hope that by working through it with you guys, I can help myself understand it better and hopefully help you guys. So first off, read the problem. Mutarotation refers to the change in optical rotation of a sugar over time as its enantiomeric purity degrades. Sugar derivatives, such as nucleosides, are also susceptible to mutarotation. Draw a mechanism for mutarotation using the steps shown in the figure. As for the product, draw the stereoisomer with the appropriate configuration inverted. H+ in this mechanism is catalytic and is provided in the product for you. So I'm going to jump right into it. Let's get into our sketcher window. Your first step is a proton transfer, and you know this is going to take place almost all at the anomeric carbon. That's where our stereochemistry is going to change. So my initial thought is this oxygen can grab that hydrogen and create a bond, and then we'd be able to eventually break this bond, and then this nitrogen's lone pair could come down here, make a double bond. Then we would be able to do an addition of nucleophile later on and have this oxygen, which is a good nucleophile, attack our carbon-nitrogen bond again and reform our anomeric product. But I'm not going to go that way because there's a much better option available to you, which is instead of this oxygen grabbing onto our hydrogen, which would be an endocyclic bond cleavage step, we could rather have this nitrogen, which is a better base, attack this hydrogen, forming a bond. We could also have attacked with this nitrogen right here, but it is not nearly as good as a base as this nitrogen because this nitrogen's lone pairs are much better equipped to grab that hydrogen. They're not participating in resonance stabilization, which is what is happening over here with this nitrogen's lone pairs. It's delocalized into this little pi system right here. And so it's going to be harder for this nitrogen to grab onto that hydrogen. So we're going to go with that and copy our product, or copy our intermediate. And then we erase this arrow, form the bond. And we have our intermediate. The next step is a beta elimination step. If you remember, a beta elimination step is a lone pair to sigma star in a pi fashion. Alright, so one sink that we have for lone pairs is this oxygen, which actually will help us in our exocyclic bond cleavage because it forms an oxocarbenium ion, which is what we want for an exocyclic bond cleavage mechanism. That bumps up there to form a double bond. That bumps out this sigma bond onto that nitrogen, and this double bond goes onto that nitrogen to give it a neutral charge. Actually, I lied to you before. This does not go onto that nitrogen. It goes on to form a double bond. With this step, we've created our oxocarbenium ion and disassociated this nucleophile. So I'm going to copy this into our next box, paste it, erase all these, add in the bonds, And that gives us our intermediate for box 3. Now we're doing an addition of a nucleophile. If you remember the exocyclic mechanism, we just simply have a reattacking of our leaving group back onto the double bond where it was before. So it would go something like nitrogen attacking, oh, it's a little touchy. There. Our nitrogen attacking our double bonded carbon. This double bond goes up onto our oxygen, and then we can undo our resonance from before by taking these lone pairs, making a double bond, taking the double bond, and bringing it onto the nitrogen. Now you're going to want to clean this up a little bit. I just used the lone pairs from nitrogen because it seems a little easier to me to think it out that way. But obviously, to say that the double bond attacks and makes the bond is perfectly alright too. So I'm going to do that now, clean it up. And that would be our addition of a nucleophile step. Let's paste this again. And it's almost exactly the same, so I didn't bother to copy it again. The only change from this to this is that the nitrogen attacks this carbon that has lost all its stereochemistry. It can now form our anomeric product. So I'm going to want to grab a wedge piece. I can think of the name. I'm going to want to grab a wedge piece, put it in there, and now all that remains to be done, I'm going to copy this guy, is to finish off our proton transfer step to reform our acid catalyst, which is just taking this hydrogen off and attaching it back to the nitrogen. And that should be it. Let's check. Oh, I see what I did wrong. Whoops. And that happens, but I'm supposed to obviously take this guy, put him there, and then, wow. And that actually happens to me a lot. I really need to slow down and think about where I'm putting my arrows, and make sure you always take a moment, look at the problem, and make sure you have electron arrows that make sense. Where are the electrons flowing to? Are you skipping over any bonds? Is the flow in the correct direction? Always be thinking about these things, and I'm probably the most guilty of this. So let's try again. And there you have it. That's the end, and I hope this was helpful, and I'll hopefully see you guys soon. Thanks for watching. Bye.